Okay, watch this. 9 out of 10 people actually get the binary conversion exam question completely wrong in exactly this way, and it quietly costs them an entire grade boundary. You do all the hard math, you write down the correct sequence of ones and zeros, and then the examiner gives you a fat zero. Let me show you the mistake right now before you end up making it in the exam hall. So let's dive straight into this trap. Take a look at what we've got on screen. On the left, we have what looks like a perfectly calculated binary number, but it's missing something absolutely crucial. When a question specifically asks for an 8-bit binary number, leaving out the leading zeros is just a fatal error. The correct format, over on the right, is 00111011. It includes those 2 leading zeros to complete the full 8-bit requirement. Without them, the computer, and more importantly, the examiner, reads it as incomplete data. It is a tiny, tiny detail, but precision is literally the only currency that matters here.
All right, so how do we guarantee we never actually make this mistake? Well, we rebuild the concept correctly, step by step. To convert a positive ternary number to binary, we carry out successive division by 2 until a 0 value results. And at each step, you record the remainder. Now here is the real secret. You read those remainders from bottom to top to give the binary value. And finally, step 4, the absolute lifesaver, if your answer is only 6 bits long, you infill the front with zeros until you hit exactly 8 bits. Once you actually see this mechanical step-by-step logic, doing it the correct way becomes almost impossible to forget.
All right, moving right along to Section 1, Visual Basic Logic Masterclass. Now, before we even look at the code, to avoid catastrophic logic errors when writing your algorithms, I need to clarify a fundamental difference that trips up thousands of students every single year. And that's validation versus verification. Validation is the computer checking if data is sensible and allowable, like using a range check to ensure an age entered is between 1 and 100. Verification is a totally different beast. It ensures data matches the original source, kind of like typing your password in twice just to double-check it. If you mix these two up in your exam responses, you are going to lose marks instantly.
Okay, looking at the image here, check out this broken answer trap on the left. Notice how just using the wrong operator, like using a strictly less than sign instead of a less than or equal to sign, completely breaks the boundary condition of the entire selection statement. Or take another super common error, failing to initialize the variable total to 0 before you start adding to it. In Visual Basic, these aren't just minor typos, they literally destroy the entire path of execution. An algorithm is really just a set of instructions, right? And if the human logic is flawed, the machine is going to perfectly execute that exact flaw.
Next up, Section 2, Demystifying Networks and Transmission. All right, so moving away from software and into the actual physical infrastructure, look at the flowing cables here. The really crucial point is visualizing the mechanical difference in how these bits actually flow. Serial transmission is just a single wire sending one bit at a time, one right after the other. It's safe, it's reliable, and it's fantastic for long distances. But contrast that with parallel transmission, which is squeezing multiple bits simultaneously across multiple channels. It's essentially like turning a single-lane dirt road into a massive 8-lane superhighway. I'm going to challenge you right now. Pause this explainer for just a second and actively predict the answer to this question. Based on the mechanical differences we just explored, which transmission method is best for short distances that require extremely high speed? Take a second and think about it. All right, did you guess parallel transmission? If so, you are spot on, because parallel transmission uses multiple wires to send multiple bits simultaneously. It is the undeniable champion for short, fast data bursts, kind of like connecting a CPU directly to memory. But remember, it's really only good for short distances, because over long cables, those bits can actually get out of sync with each other, which is an issue known as data skew. Now, when we're connecting all these devices together using network topologies, we really have to compare two distinct models. A broadcast network basically acts as a one-to-all model. It's incredibly simple, but imagine everyone shouting in a crowded room all at once. It creates massive congestion risks, which we call broadcast storms. Contrast that with point-to-point networks. These are dedicated direct links between specific devices, and they allow full duplex, simultaneous bidirectional data transfer. Yes, it's definitely more complex to wire up, but it offers vastly enhanced privacy and zero shared line congestion. Moving on to Section 3, Logic Gates and Architecture.
We're zooming way in to the microscopic level now to understand the exact hardware logic that processes all this traveling data. Let's track the Boolean mechanism through these glowing data streams. It always follows a very specific three-step path. Step 1, digital circuits receive binary data as the initial input, the raw zeros and ones. Step 2, the logic gate applies a specific Boolean operation to those inputs, like an AND or not rule. And step 3, the circuit generates a resulting single binary output based on that applied rule. If you want full marks on the exam, do not just state that a logic gate makes decisions. You've got to explain this exact input, process, output mechanism and anchor it to a real-world scenario like an elevator control or a security alarm system. Now, check out how the disciplined path to application shown here connects all those microscopic logic decisions to actual data movement. Data doesn't just teleport, right? It travels along physical hardware buses. Mastering this means you have to explain the logical sequence, how the address bus finds the location, how the control bus manages the signals, and how the data bus actually moves a physical payload. If you leave out any single step in that sequential explanation, you are going to drop marks. Let's jump into Section 4, Securing Online Communications.
Okay, let's zoom back out from the motherboard and into the World Wide Web to tackle the protocols that keep all these data packets safe from interception. Focus on the center here. When looking at common pitfalls, you have to remember that examiners severely penalized generic labels. If a question asks why a retail website uses HTTPS and you just write, "it makes it secure," you get 0 marks. No way around it. You have to anchor your explanation to specific digital scenarios. You need to explicitly state that HTTPS encrypts the data using SSL or TLS protocols, ensuring that sensitive information, like a customer's banking details or their credit card number, cannot be understood if it gets intercepted during transmission. Context is absolutely everything.
Right here on this slide, we're breaking down what we call the 3-layer mastery framework for packet switching. This guarantees you don't skip any steps in your exam response. First, we have packet creation. The data is broken down into fixed-size packets, and each one is given a sequence number and a destination IP. Second is routing. Routers send these packets across different optimal paths based on the current network traffic. And third, destination assembly. The packets arrive, often completely out of order, by the way, and are reassembled into the original file using those sequence numbers. Memorize that 1, 2, 3 sequence, and you're golden. If you look at the bottom right here, we're going to review the exact corrections you need to make to transform vague wording into context-justified A-grade exam responses. Instead of saying something simple like a router sends data to the internet, you need to upgrade that to a router directs data packets between different networks using IP addresses. It's all about moving from just a basic description to really explaining how it works and why it matters for the user in that specific scenario. Finally, we have Section 5, the Exam Survival Guide. We're bringing all these technical blueprints together for a final masterclass now. And I really need to emphasize this ultimate rule of exam survival. 1 mark equals 1 point. Waffling just wastes your time. If a question is worth 3 marks, the examiner is actively hunting for 3 distinct, separate technical concepts. Rephrasing the exact same idea 3 different ways will only ever earn you a single mark. Like I said earlier, precision is the only currency that matters. And to actually secure those specific marks, we have to decode the Cambridge command words. If a question asks you to state or define, they just want a concise technical definition. Easy. But if they say explain and you just give a definition, you lose the marks. Explain requires the why or the how mechanism. And if they say compare, you must explicitly provide characteristics from both sides of the technology to show how they relate to one another. You have to play the game exactly as the command words dictate. So there you have it. That is exactly how you transform a broken 0-mark answer into an examiner-approved top-band response. If this explainer made things click for you and you want to keep crushing it, make sure to subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to guarantee you excel in all your Cambridge examinations. Before we wrap up, I'm going to leave you with this provocative final thought to chew on. We've seen today how just a missing 0 in an 8-bit binary conversion can completely crash a simple program, but what do you think happens when a single flawed logic gate physically takes down an entire global network topology? Just think about the catastrophic, cascading failures that would cause. We are going to rip into that exact crazy scenario in our next explainer on advanced system vulnerabilities. You definitely don't want to miss it for sure. See you there.